All right, we are very happy to have Mandy Cheung, and she's going to talk about polytopes, wall crossings, and cluster varieties.
Okay, thank you very much for the invitation. It's such an honor to give a talk here. But I must say I miss the Simon Center, especially their accommodation and food. Let's hope we can have it next year. Today I'm going to talk about polytope wall crossing and cluster varieties, which there is this, is it going down? Sorry. In September, it's like previously in the four theoretic and algebraic geometric aspect of SYC Mirror Symmetry Conference in this September. In the first half of my talk, in that conference, I was talking this joint work with Lucian Lin. And then at the end of the first part of my talk, I claim that with Lucian, we interpret the Gross-Hawking-Q mirror construction in terms of the family form mirror and get the mirror for rational elliptic surface as DP5 and DP6. And once I did that claim, there's like this audience here, which is Professor Mark Ross, immediately asked, do I just get the whole open piece or do I get a compact thing? Which he did point out. I cannot reclaim that I got DP5 and DP6 instances. I just get the open piece. But why do I make this claim of we can get something that can compactify to DP5 and DP6? And that is the motto of today, which is given this open piece, how can we talk and describe the compactification of it? So as to refresh our mind, I will start with recording what we have in the September conference, which is Abigail and Mark. Abigail talked about yesterday and Mark go over that today already, which is this 2011 Gross-Hawking-Q mirror construction that start with a log-Calabi-Yau pair, because like here is 2 dimension. We have a smooth complex projective surface, and then we have anti-canonical divisor with all the properties there. And from this log-Calabi-Yau pair, we look at the tropicalization of it, which we have this B and alpha integral manifold, as Mark talked about today. And then again, like in the talk, Mark, he got this cone, which is we have a cone decomposition of B. And then in September, I even directly copy and paste this picture in my talk in September, which is, this is the example we will have throughout this talk, which is we look at DP5 and a train of 5 minus 1 curve. And then there we look at the dual intersection complex, and then we can obtain a cone structure like that. But then the thing is, when we go back from the 5th divisor to the first one, we have this piece that we need to glue along, and that is how we induce this affine manifold structure, which is we have a monoidromy over it. It's not just R2 or C2. So this is our, sorry, my computer keep on flipping, our tropicalization of this log-Calabi-Yau pair. And then the next thing, again, as Mark mentioned today, is we subdivide the cone. In this case, we didn't, but then we have this wall structure, which is on this affine manifold, which is, this is dimension 2. So we have a way that with a rational slope weave, and then we have this function that is polynomial or power series if we push to infinity, that is in terms of exponent of that direction. And then here in Mark's talk, he already tells us that the coefficient here, or log of this FD, then we have this coefficient coming from some gamma written invariant. Again, it's an ongoing example. And like Mark said today as well, Gross-Hawking-Q showed that this canonical consistent scattering diagram are consistent, which allow the gluing is well defined. We'll later on say about it. Well defined. But then as an example is we have this cone decomposition in the last slides. And then here, those are the wall function that we associate to this cone decomposition of this scattering diagram. And then here, the next thing is in Mark's talk, he was saying that we associate to each cone he associate. I was directly copy and paste from his talk today. This curve class, and then more outer ideal, and then none lattice. But then if you take enough reduction, then actually we are just taking the spec of the k to the lattice spec of the polynomial power series, so we get algebraic torus. And then what we have is here is we associate each chamber, the maximum cone of the scattering diagram, with a torus. And then here we have the wall here. We are going to say that will give us a path order product or wall crossing. And then we glue each torus by this path order product. And then we obtain this excerpt. And then the last step, we'll talk more later in the cluster setup, which is we'll define for each point Q in the integral point in our affine manifold, we'll give or GHK define this global function, the theta function of the space, and then the proposed mirror will be, and then they show that the theta function will give the vector space generated by the theta function carries a algebra structure that we can take the spec of it, and then we'll construct the partial compactification of the space we construct, and this is the GHK mirror. And then this is what the GHK Gross-Hawking Q mirror construction is doing. And with Yushan, what we do is we just verify the dictionary between the algebraic geometry world and the synthetic world, which is we show that for rational elliptic surface of certain type that you are going to see here on one side, this is the steel intersection complex that we were just describing, but then we show this is the base of the SYC vibration with the complex affine structure, and then the waves are the holomorphic Maslov index zero holomorphic disk, and then the function using actually Yushan-Lin's result that correspond to the Gromov-Witten invariant of Maslov index zero. And then there's detail that is in the September conference that I'm not going to repeat, but then here when we do the gluing of the algebraic torus, that is actually corresponding. And I don't know why my eraser is not working. Okay, I guess some technical issue is here. And then here what we are doing behind this, we are thinking the Maria-Cartan space induced by the isomorphic, and then we have the wall crossing as actually dictating the change of the A infinity structure of the Maria-Cartan space. And then here on one side we have the Gross-Hawking Q mirror, on the other side it is the family 4 mirror proposed by Fukaya, and then later on with the work of Abusai and Tu and many other people as well. So with Yushan, what we do is you are going to see it is very standard is in the cluster picture, which I cannot write again. Yes, which is on one side we are looking at the polynomial ring, Lorentz polynomial ring, and then we have the torus, and then we glue the torus by the wall crossing structure or wall structure. And then in the synthetic side, we just switch the algebra to Tate's algebra. And then there we actually kind of in the analytic geometry sense, we take the spec of it as well. And then we have analytic torus. And then we just do the same thing, which is we go through those analytic torus by the wall crossing, which here is actually kind of easy because you can see in the case we are going to have the wall crossing are just algebraic. So we can use Gaga to lift up the gluing from here to the analytic side. So with Wilson, this is what we have. It's a very long statement. But what we have is we have rational elliptic surface, 3 of them with either singularity 2 star, 3 star, or 4 star, and then we have a Kähler rotation, hyperkähler rotation of it to switch the base to R2, but not complex. And then what we claim is we have our Fermi mirror of this free space, which has the compactification, which are the identification of dp5, dp6. And at that time, we haven't worked out the G2K yet, but here now we have fully worked out the type G2 yet. So we obtain this free thing. But you can see here, this is how this picture comes in, because like we are having an open piece, and then it would be nice if we know about how to compactify all the whole mirror is. So this is the starting point of today, which is we want to compactify. And like the things looked at is, okay, that might be redundant, but if we look at the torus, even just C star, this is not compact. So we want to compactify it. And then the idea of today is we go back to the setting in toric geometry, projective toric geometry. For example, we just look at CP2, which we are looking at the homogeneous coordinate is just the greater ring. We are looking at the homogeneous polynomial in this free variable, which the degree 1 monomial can be put in this polytope or triangle like this. And then the degree 2 monomial, you can see here, it's just C0 square or C0 C2, which can fit in this triangle, which you can see here is the dilation by 2 of our original one. And then if we go ahead, move forward, and look at our degree 3 monomial, you can see actually we are repeating doing the same thing. We are looking at the dilation by 3 of our original polytope, and you can see here all the degree 3 monomial just fit in at the vertex of this 3 dilation polytope here. And the thing is, actually, this is not a coincidence, which is a very general construction in projective toric geometry. What we can do is we can put this polytope one higher dimension up, and then we look at the cone over it. And then we can see that actually the degree 2 and degree 3 monomial, the corresponding polytope satisfy at this layer 2 and layer 3 of the cone. And so this is what we have, which is this projective toric variety construction is we start with a convex lattice polytope, and then we can have a greater ring, which here you can see the grading is given by the dilation of our convex polytope. And once we have a greater ring, as an algebraic geometer, we take the spat of it, so we can obtain this projective toric variety. So here now go back to cluster variety, which we have go over that as again in the September conference too. So let me be quick and just say that they are just as schooling torus by some birational map given by this cluster transformation, which actually we'll call mutation map. For example, one of them is x maps to 1 plus x maps to x times 1 plus y. And the reason behind last time we give this reason is we can go over the video and chat, which is the bow up of, it's just like this 1 plus y is nothing, just bow up of toric variety. And then here, but I just want to say here, this schooling can be described by this cluster scattering diagram, which we fix a lattice. And oh, by the way, one remark here, we kind of touch off it. They are like going to have, in the cluster theory, there's a 2 type of mutation, which we are called the A mutation or X mutation. And using the 2 different type of mutation, we'll get A or X cluster variety, which we might pop up with those notions later in the talk. But in terms of scattering diagram, but they are all can be described by some sort of scattering diagram, which is we start with the lattice, dual lattice, tensor R of each of them, and then cluster scattering diagram is a collection of wall with some condition. Actually, Mark have mentioned today, which is if you mark out I, it is the maximal ideal, it is 1, the only constant term is 1, or if you mark out some ideal I that is the radical is m, then you only it is the polynomial we are going to see is only a polynomial. And here we are not going to touch too much about consistency, so I will assume the cluster scattering diagram already have this consistency condition. And here a wall here is what we have in a couple of slides ago, but here is more is for general dimension. That is, we have still way in dimension 2 we have a way. In higher dimension, it's just a convex rational polyhedral cone of codimension 1 that it lies in a hyperplane. Here is contained in n per where n is in n. And then we have this function similarly as before, but here here it is will pick this direction in the hyperplane, and then it's a polynomial or power series in this direction. And actually we also have kind of touched it in Mark's talk of question, which is here for cluster variety, they contain a toric model. So the underlying affine manifold is just R2, the lattice is just it's just Rn. So here we do not have monoidromy of the underlying affine manifold structure. So this is, you can see we are all just paying the same example. So this is our A2 cluster scattering diagram, which we again just have 3 walls. And then here the function here just correspond to the direction on the hyperplane. And then what we have next is this path order polar or wall crossing transformation, which is we consider a path that crosses over a wall D, then we can define a mapping on the monomial, which as an example to illustrate this formula, it is something like this, is our scattering diagram, and we have this gamma passing over this wall. And then when we apply this path order transformation, say on this C-1, 0, what we have is we keep the same thing, and then we multiply the wall function to some power. Here we are interpolating this m, which is -1, 0, to this normal of the wall, which is we choose this direction here. So you can see after the interpolate, we got a 1. And I'm not sure if there are cluster people here, but we can expel this formula. It will be just 1 plus A2 divided by X1. And one can see here, this is actually the cluster exchange relation. But here, like in Mark's talk, the way we are going to see here is we have a torus associating to each maximum cone of our scattering diagram. And then like we keep on saying before, we glue the torus by the path order polar. And then here in this case, here we glue it in this case because this is the scattering diagram correspond to the type A2 cluster case. So we got the A cluster variety. So this is how we have for the definition or like a way to describe the cluster varieties. And then it is, as we mentioned in the Gross-Hawking Q mirror construction, the other ingredient we need is this theta function. The motivation, if you are not used to it, the motivation we can think is if we just look at the torus and then the coordinate ring can be just generated by the monomial, the toric monomial, where the monomial can be just indexed by the C2 lattice. So this is the thing we are thinking, which is at each lattice point on our scattering diagram, we associate a function to our cluster varieties. So sorry. So here is what I say to each integral point in my lattice other than the zero. We associate this theta function, which is defined by something I call Booker line, and this Booker line consists of two data. This defined by two data, which is if it is theta m, I will have this initial slope and endpoint q, and then the definition is very long. Again, let me illustrate that by an example. Let me now choose my m is -1, 0, and I choose my endpoint q here, which Booker line, first of all, is just a line here with the direction given by this initial slope. Here is -1, but then I go in opposite direction. Endpoint here just mean my line end in this point q, and then I go into opposite direction. So -1 here just mean 1, 0 here just mean I go in this 1, 0 direction. And then I have this monomial associating to the line, which just mean my direction. And this is my Booker line already. And it doesn't mean exciting because I got the term Booker here. Booker just means it bend over a wall. So this is the second example. I have a monomial and this initial direction. And then when I bend over a wall, that just bend according to the data of this wall function. As in the calculation we have before, in this case here, it's just -1, 0 plus 0, 1. So I have this direction, -1, 1, which it will arrive at this q as well. And here as a remark, for the later on for the computation, you can see because of going in opposite direction, like here for this wall, you can see I have 3 arrow on this getting diagram because this wall is like 0, 1, and 1 plus set to the -1, 0, and 1 plus set -1, 1. And this is the point 0, 1, and this is the point -1, 0 here. And you can see here it's only when the Booker line bend over this way containing this point, it will bend towards the origin. If I have a Booker line here, it will bend away from the origin. So these two pieces, I will call them incoming. And those 3 pieces is called the outgoing. And then here is my theta function. Okay, I talked so much, I haven't talked about my theta function. My theta function with this data q and initial slope is, I look at the collection of all Booker line with initial slope n and endpoint q. And you can see because, as I said here, I bend out. So to arrive this point q, those are my only 2 Booker line. And then I look at the final monomial and then I sum it up, and this is my theta function. So again, as said in the Gross-Hawking Q mirror construction, one thing they show is theta function has an algebra structure. That is, we can multiply 2 theta function and express it in terms of linear combination of other theta function. And this is our structural constant here. And then once Gross-Hawking Q's, we have this consideration, this multiplication formula that just induce a algebra structure to the vector space generated by theta function. And in particular, for the interest of today, this structural constant can actually express in terms of Booker line. This is a very long summation over this long data, but actually it's very easy to describe because those are the coefficients of the final monomial. All we are looking at is we multiply P and Q. So we look at a pair of Booker line with initial slope P and Q. Endpoint, it ends on the theta out, it appears here, and it satisfies some balancing condition. So again, let's just illustrate by an example. We can just do brute force and calculate the multiplication between these 2 theta functions, and then we'll obtain it is summing up this theta 1, 1 and theta 1, 2. But in terms of this Booker line language, you can see here, I can have this Booker line here with this initial slope coming here, and this Booker line here with initial slope coming here. And then I can we can arrive to this endpoint and satisfying this balancing condition. So you can see here, that's why I have this coefficient 1 here. And so here what we have is we can express the multiplication structure of theta function in terms of broken lines. And here I want to draw an analogy, because you are going to see in my talk flow today, I always want to go from the toric world to the cluster world. And weakly speaking, the fan in the toric world are just our scattering diagram. Toric monomial are just theta function. And then in the beginning, we mentioned about the projective toric variety are given by convex polytope. And in the cluster world, it is given by something called positive polytope, which is defined by Gross-Hawking Q conservation. What that is, if we have a set is positive, if here, let us go back and look at the multiplication formula. For P is at the 8th dilation of my set, Q is at the bth layer dilation of my set. If I have R appearing on the right-hand side, I have my R is just in the A plus B dilation of the set. You can see this one is nothing, but just literally write out the cone construction or the grading we just have before in the toric case. So you can see once we have a set is positive, we have give a compactification or partial compactification of the algebra generated by theta function. So here is it. We were talking about the first B3 generalization from toric world to cluster world. And then in terms of convexity, convex is defined by line, because convex polytope is given 2 points. The line that join the two points will lie entirely inside the polytope. And here we propose a line should be a broken line. And so convex should be something we call broken line convex. So with Tim McGee and Alfredo Lajetta Sheffield, we define a set is called broken line convex if for any 2 points in our set, every broken line segment will contain in the set. And then, as you might imagine, the theorem we have is a set is positive. That is a set that gives us the grading is if and only if it is broken line convex. And the way to prove it is simply that in the beginning, when we were talking about the structural constant are expressed in terms of pair of broken lines with initial slope P and Q. But you can see here when we define this broken line convex, we look at the endpoint of broken line segment. So the proof is basically we write down this correspondence between pairs of broken lines and broken line segment with endpoint PQ and R. So you can see once we establish this correspondence between broken line and broken line segment, we can immediately deduce the result. So as a consequence, we have a broken line convex set, we have a graded ring, and then we can take report of it that we have a compactification of the cluster variety. And then as an example, this is our keep on ongoing A2 example, and actually this example appeared in Gross-Hawking Q consideration already. We can all look at all the primitive generator of our wall or way, and then we take the convex hull of it, and this polytope is positive, which you can see here. I have 5 lattice one, or you can do all the calculation of -1 curve, but then we can see here, this is the diapason surface of degree 5. And then once we have A2, it's like my work with Yushan, and then how about B2? And B2, like the scattering diagram is like this. And then we can just do the same thing, which is we look at the primitive generator of the waves, and then we look at the convex hull of it, and then we can immediately use the theorem to check this is broken line convex as well. So we know this is positive. And with Tim McGee, we find out that this is, or you can see already that this is the diapason surface of degree 6. I just want to say the theorem with Tim McGee and Alfredo's photography, it might seem very short, but like actually determining if a set is positive or not, if you do not use spoken light convexity, is highly non-trivial, which like from 2014 Guosong Q Conseil, they did the A2 case. No one have ever really even just do this B2 case. And so, and even when with Tim, when we first try to compute this, we need to use the root system of B2 to deduce the result. So you can see now with this spoken light convexity, we can just check if the set is positive or not almost immediately. And then A2, B2, the next question is, how about we just do the same thing in G2, which this is our G2 scattering diagram. And then you can see here, if you just look at the primitive generator, the polytope itself is already not convex, but you're like, okay, I just take the convex whole of it. But then when you take the convex whole over here, actually this polytope is not spoken light convex. The reason is here, I have this wall function is 0, 3 because of G2. And if I contain this power minus 1, 0, and 0, 1, 0 here, because here you can see I changed the slope by 0, 3. So I will have this spoken light segment that passing through this point 0, 3 half, but it will have the endpoint minus 1, 0, and 0, 3. So you can see for this polytope, we need to carry the non-integral point, a rational point. And one thing I was talking about is in the beginning about spoken light is I mentioned about incoming and outgoing wall. And actually, you can see it because for outgoing wall, my spoken light always span out. So you can see how easy to check spoken light convex, which is I only need to check over the incoming wall in this two-dimensional setting. So you can see that is why we know that if there's like rational point, it will definitely come either this side or that side of our polytope. But then here comes the question, if you are toric people, or polytope people, you might be unhappy now, because usually we just think about lattice polytope. But now I'm telling you that we need to consider this non-integral point, rational point. So the question is, do we even really care this proposal that with Tim and Alfredo we propose? I just want to give you one evidence. I consider very strong evidence, which is from Guasmanian. Quick revision is Guasmanian is the space that parameterizes all k-dimensional vector. Oh, I even have spelling mistake. Sorry. Vector subspace of the n-dimensional vector space in Cn. And then Scott showed that the coordinate ring of affine cone of the Guasmanian carry the cluster structure. So actually Guasmanian are cluster varieties. So we can put back all the machinery we have before to this Guasmanian world. And then Rich William showed that in the paper mirror symmetry for Guasmanian cluster duality, they show that for Guasmanian Kn, this is, we are going to go over the definition later, but the statement is this Newton O'Connor body to the X variety, which actually the A and X variety, in the Guasmanian case, they are all Guasmanian, either girl Kn or girl N minus Kn is equals to the tropicalization of superpotential of the A variety. And then here maybe I should say was talking Q consideration, but you can immediately tell it already, but here you might want to have some P-star map. And actually the two polytope in our sense, in this scattering diagram, they are just a positive polytope. That is using the theorem, they are just spoken light convex polytope. And then what Rich Williams showed in the paper is this Newton O'Connor body, no body, is a rational polytope. So, but the thing is, are they integral polytope, which is not? That is this example actually computed by our collaborator Lara Bossinger, which when you just go to the low body calculation, you get rational slope. But then we show that this rational slope rational vertex just come from the Bokenite convexity. And this is a slice of the scattering diagram of growth 3-6 with a choice of initial torus chart. There are many notation here, but all in all, we are just mapping the Pucker coordinate by valuation to the lattice point. But then here is this calculation is almost exactly like what we did in the G2 case. We have these two vertices in the polytope or in the set, and then we want to bend over this wall, the wall crossing or exchange relation, but we bend over it by checking the Bokenite segment. We have no choice but to pass through this point, which is a rational point, which is not integral. And you know, like by the point this example is it's just using computer, people know that they need to carry that rational point. But you can see by putting all those things in this scattering diagram and Bokenite convexity, we can fully explain why this rational point is necessary in the setup. So here comes, I hope it's not too technical, but especially we touch it at the in the morning session. The definition of Newton O'Connor body is we look at the Grassmannian and we look at the anti-canonical divisor actually given by Puckers, and then we look at the open piece of it, and then the next thing is, like Michael said, we have the choice of ample divisor and a choice of valuation. And the nobody for this divisor is we look at the section ring of it, the valuation of the section ring with a scalar ring, and then we take the convex hull of it, and then take the closure of this convex hull. And then what we propose now is, instead of taking convex hull, we should take Bokenite convex hull. So what we do now is, we have this valuation given by theta function. Like here, theta function is defined by, we look at each point, the lattice point, we have the theta function. But now what we define is, if we have a choice of the, if we given a choice of the initial torus, then we just map the theta function back to the corresponding topical point. Sorry. And then now, given a function which can be expressed as linear combination of theta function, we define the Newton theta function analog of the Newton polytope of F, which here you can see we are doing nothing. If we forget the BL, we are doing nothing but just looking at the Newton polytope corresponding to the basis given by theta function. But now what we have is, we look at the Bokenite convex hull of those points. And then what we define, we call them the intrinsic Newton O'Connor body, which is, we are like basically doing the same thing, but then here is we look at this theta function Newton polytope, and then you can see here we're just like in the definition of no body, we have this scaling, we are just doing the same thing. And you can see we can kind of recover the original definition, because here once we fix the choice of the torus chart, then we can identify this valuation with the usual variation. And then we define again here for all the convex hull, we take the Bokenite convex hull of it. But then what we show here in the usual no body definition, we need to take the closure. But you can see here, because we know, like Rich Williams showed, that this no body are just positive polytope. And we know positive polytope are Bokenite convex. So we know immediately that actually we do not need to take closure of it. It is just that this is just a Bokenite convex polytope. And then as a consequence, which is we can in particular choose the valuation given by the Pucker embedding, and then we can look at how we evaluate the Pucker to our lattice, and then there we look at our Bokenite convex, which we have our no body can be expressed in this way. You can see it's here like once we have the correct setup, everything's just like follow with this spoken like convexity setting. And then the next thing I wanna go over is this work in progress or a dream that Tim McGee and I we are looking for this final Landau Ginsberg mirror construction. In the toric world, what we have a fan, and then we look at the canonical divisor, and then the potential are just looking at the sum of the monomial corresponding to the result component of a divisor, and then it's kind of the better raw picture as well. So we look at the hypersurface, which we see them as the level set of our potential. And then to look for the mirror space, we look at the Newton polytope of our potential, and we look at the toric variety of that polytope. And then in the toric case, like the section of the two spaces of those hypersurface to be mirrored to each other. And so now we switch to the Castor world. If you remember the table I draw in previous slides, a fan to us now is a scattering diagram. So now we have a final minimum model, and then we have this anti-dynamical divisor, which here are corresponding to our dimension 1 cone in the scattering diagram. And now here we have toric monomial. Toric monomial to us now is just theta function. So now the potential are just a sum of theta function. And then here we just like think the same thing, not changing. But then at the end, this last step, when we look for the polytope, we propose it should be the theta function, theta Newton polytope of our proposal, of the potential. And then we are hoping some mirror statement out of that as well. And then the next thing, it is very nice that we bring it up in the morning of the talk, which is as we bring this up in the morning session, maybe we spend a bit more time on it. In the Castor world, in the Castor algebra or Castor variety setup, the definition used to start with a seed, either in the algebra world is a set of and many variable, or here in the geometry world we see them as torus. But then it can also be seen as the spec seen as given by a basis of the lattice, where there it gives the ring, and then when we take the spec Laurent polynomial, when we take the spec we get the torus. And then here in the Castor world, with a seed, we always have this mutation step to get another seed. So the setup of how we get the scattering diagram is, given a seed, we associate this scattering diagram to it. And so here, the thing here is in the development, in the work of Gross-Hawking Q conservation, given a seed, we define this scattering diagram. And actually, when we mutate the seed, the corresponding scattering diagram, they are not equivalent to each other, but they are equivalent up to a piecewise linear map. Here at TK with a piecewise linear map. So here, for this picture, you can forget my polytope first. Like here, let me start with this scattering diagram. Correspond to one seed, and this one is actually correspond to when I mutate my seed. And you can see here how my piecewise linear map go. I kind of fix a half plane, and then here I do a shearing to the other side, and then I obtain this pieces of wall from this one, that one to here, there. So this is how we have for wall crossing or mutation of the scattering diagram. And then here, if we start with, if we have this positive polytope, on this scattering diagram, you can see it mutate accordingly to according to this piecewise linear transformation as well. So here you can see we do obtain some mutation of polytope according to the mutation of seed or mutation of the scattering diagram structure here. But here is in it might matter in geometry sense, but here in some sense it is not too exciting in terms of competitive application sense. Reason is here this wall crossing here is nothing but change of variable. So you can see all the polytope I got are just pentagon, and they are all just DP5 in some sense. All of the space I got here are just isomorphic. So here I actually propose another type of mutation that actually kind of come from what we have in the beginning when we talk about this affine manifold in the Gross-Hawking Q-mirror construction. And this is my scattering diagram in the geometry point of view, which is we have singularity at the infinity. You can see here, this is how we can see it, because those are the incoming walls. And then the thing is, we might move the singularity here to the origin, and then convert this incoming wall to the outgoing wall in the scattering diagram language. But then when I do it, actually I induce a affine manifold structure or induce a monodromy to my underlying space. And here what I do is like in our beginning example, I kind of cut out this cone and then glue them together for DP5 and this dy. And here I cut out this one and glue them together. And this is the monodromy. Here is I explicitly write down the monodromy of the underlying affine structure here. So so here what we have is originally I have this polytope here, which I mutate according to this change of the affine structure, which you can see here. I kind of cut out this cone. That actually I'm doing some shearing as well. You can see I'm doing some shearing of this polytope to the other one, but it's not in the cluster mutation sense. If you go straight back to the definition of the cluster scattering diagram, but what we have is here is we can go back to the mutation cycle. You can see here, this is I kind of flip here, which is I have this polytope here, and this is my shearing. And then here, actually, all the four remaining is the same custom mutation we have, because like here, you can see I do the shearing in this way and the other way, and then I loop around, have this cycle of mutation of polytope here. And then what we have with Vienna Renato is he come from another very different perspective, which is looking at the almost toric vibration that he add the singular Lagrangian fiber to his vibration. And what we check is we end up having the same cycle of mutation of polytope here, and that you can see here. This polytope actually we can go back and synchronize with the synthetic world. And what's more is actually in Vienna's story, he also have polytope with rational pawn as well, which actually fit, you can see in the example, the G2 example we got in the very early of today's talk as well. And I'm really sorry, but maybe let's end slightly earlier, and that's the end of my talk. Thank you very much for listening.
Thank you, Mandy.
Thank you.
So any questions?
I have a comment, more than a question. So I wanted to comment that I think this general phenomenon that somehow breaking points or broken lines if I understood correctly, you're suggesting that they correspond to vertices of occult bodies in some sense. I think it should be quite general in the Fano case, even
It should be
beyond
general.
the-
Like,
Wait,
even though
just-
I wrote it is Grassmannian, it's not. It
Yeah.
just, you can see, it just fit actually.
Yeah, but even beyond the cluster case, because I think we know in general that I don't have a great intuition about scattering diagrams beyond the cluster case, but I think it's true in general that these breaking points have rational coordinates when you read them in a given chart. Correct me if I'm wrong, and it's also true that if you take a Fano manifold polarized by an anti-canonical divisor, a Tark degeneration of that as polarized variety will be in general a Q-Gorenstein Tark Fano. And so those have polytopes that have rational vertices as opposed to lattice vertices in general. So I think it's really a general fact, and it's also quite special in the sense that occult bodies could have vertices with quite general coordinates if they don't somehow relate to Tark degenerations. They don't need to be rational in general, but in this case they are. So I think it's quite a general phenomenon.
No, I agree on that. It's like we just need to write it down. Yeah, like you can see, as long as to me, as long as I can put a scaling diagram there, then it should just fit in.
And presumably the broken non-convex hull is always as rational vertices, I assume, because
Right.
everything, I mean, the construction of broken lines is essentially rational construction.
Yeah, because so if I understood correctly, because the speed, the direction is integer, right?
Yeah,
And the walls are, I mean, integer. I mean, dual to integer vectors, and so somehow the intersection is rational.
Yeah, exactly. But the thing is, this incoming and outgoing, if we go to higher dimension, is, I think we can do it, but the thing is, you can see it getting subtle. What's meant by bending towards the origin? But you can see here, there's many ways you can, even for higher dimension, you can reduce to this just 2 dimension. Like for this Grassmannian, like it is a much higher dimensional scattering diagram. But the thing is, we kind of know what are the incoming ones, and then you can look at the slice of it and then check it as well. But it's only like for higher dimension, if you just like the wall will be hyperplane, and so it's like need some word to define what's meant by bending towards the origin. But you can see here, even like we can just check. If you just want to check a vertex, then you can just take a slice, and then you can verify that by the 2-dimensional picture.
Other questions or comments? Okay, thank you, Mandy. I'm gonna stop the recording and people can continue talking. We're gonna start the next talk at 3:30.
Should I stop?